Welcome to this module on Infrastructure as a Service, the first layer of cloud computing with Microsoft Azure. In this session, we'll take a deep dive into three foundational pillars of Azure: IaaS, Azure Virtual Machines, Azure Load Balancers, and Azure Virtual Machine Scale Sets. By the end of this module, you'll understand how to deploy and manage virtual machines in the cloud, how to achieve high availability using load balancers, and how to implement horizontal scaling using scale sets, one of the most powerful benefits cloud computing has to offer. This is an essential stepping stone for anyone moving workloads from on-premises environments to the Azure cloud. Let's get started. Let's start by grounding ourselves in what infrastructure as a service actually means. IaaS is the foundational layer of cloud computing. Instead of purchasing, racking, and cabling physical servers in your own data center, you rent virtualized compute, storage, and networking resources from a cloud provider like Microsoft Azure. Look at the cloud responsibility model on the right side of the slide. With IaaS, you are responsible for everything from the virtual machine upward, the operating system, middleware, runtime, and your own applications. Azure, on the other hand, manages everything below the hypervisor: the physical hardware, networking, switches, power, cooling, and the virtualization layer itself. This is the key benefit. You get the flexibility and control of managing your own server without the capital expense of buying hardware or the operational burden of maintaining a physical data center. For organizations migrating workloads to the cloud, IaaS is the most natural first step, because managing an Azure virtual machine feels very similar to managing a local server or a VM in your on-premises environment. The tools, techniques, and responsibilities are nearly identical. When it comes to deploying Azure virtual machines, you have several options, and the right choice depends on your use case. The Azure portal is a web-based graphical interface that's perfect for learning and for one-time deployments. It's visual, intuitive, and gives you immediate feedback on what's being created. We'll use the portal as our primary tool in this module. ARM templates, or Azure Resource Manager templates, are JSON-based declarative files that describe your infrastructure. They're ideal for repeatable, version-controlled deployments, especially when you want to ensure consistency across environments. Azure PowerShell provides scripted automation through PowerShell connects. If you're a Windows administrator already familiar with PowerShell, this will feel very natural. And Azure CLI is a cross-platform command line tool that works on Windows, Mac, and Linux. It's excellent for CI and CD pipelines and automation workflows. Throughout this module, we'll primarily use the Azure portal so you can clearly see what's created at each step. For automation scenarios, we'll also look at ARM template examples. Creating a new Azure virtual machine in the portal involves three main stages. In the first stage, you select an operating system image. Azure offers hundreds of images spanning both Windows and Linux. Supported Windows server versions include 2008 R2 SP1, 2012, 2012 R2, and 2016. For Linux, you can choose from Ubuntu, CentOS, Red Hat Enterprise Linux, Kali, and Oracle Linux, among many others. Interestingly, as of 2017, more than 40% of all Azure virtual machines were running Linux, and that number has only grown since then. You can also choose pre-configured images that come with additional software already installed. For example, a Windows Server 2016 image with SQL Server ready to use, or a Linux image with configuration management tools like Chef, Puppet, or Jenkins pre-installed. And if you have an existing on-premises VM, you can upload and use a custom image. In the second stage, you provide basic information, a meaningful name for your VM, like WebSRV1, to indicate it's a web server, your disk type, a username, and the subscription, resource group, and location for deployment. One important security note: Azure does not allow common usernames like admin or administrator. because many Azure VMs with public IP addresses can be reached via remote desktop. Using predictable usernames makes them easy targets for brute force attacks. This restriction helps protect your cloud resources. In the third stage, you configure size, high availability, storage, networking, extensions, and monitoring, which we'll cover in detail in the next slides. Choosing the right VM size is one of the most important decisions you'll make. During deployment, the size determines three things: the number of virtual CPUs, the amount of memory, and the type of OS disk available. There are three pricing tiers. The basic tier is designed for development and test environments. While performance is similar to the standard tier, basic VMs have lower IOPS and don't support load balancing or auto-scaling, so they're not suitable for production use. The standard tier is for production workloads. It provides better CPU performance and higher IOPS and supports all Azure features including load balancing and autoscaling. The low-priority tier leverages unused capacity in Azure data centers. It's significantly cheaper, up to 80% less, but Microsoft can reclaim these resources at any time to satisfy higher priority requests. Use this only for batch processing and non-critical workloads. Within the standard tier, there are 6 specialized categories. General purpose offers a balanced CPU to memory ratio and is the most common starting point. Compute optimized has more CPUs relative to memory, ideal for web servers. Memory optimized has more RAM, great for in-memory databases. Storage optimized offers the highest disk throughput and IOPS. GPU VMs are purpose-built for graphics rendering and video editing. And high-performance compute VMs have at least 8 virtual CPUs and use DDR4 RAM for demanding scientific and engineering workloads. One often overlooked consideration: the VM size also determines how many network interface cards you can attach, ranging from 1 to 8. The third blade of VM creation contains several critical settings for high availability and storage. For high availability, you have 2 options: availability zones and availability sets. An availability zone places your VM in one of several physically separate zones within an Azure data center. Each zone has its own power source, networking, and cooling infrastructure. If you're running a critical service on multiple VMs, spreading them across different availability zones protects you against zone-level failures. An availability set works at a lower level. It distributes your VMs across multiple physical servers, compute racks, storage units, and network switches. Beyond hardware protection, availability sets also signal to Microsoft that these VMs need to remain operational, so Microsoft will never perform maintenance on all VMs in the same availability set simultaneously. Here's a critical point you must remember: these high availability settings cannot be changed after the VM is created. You must define the availability zone and availability set at creation time. If you forget, you'll need to redeploy the VM. On the storage side, you choose between HDD and SSD. HDD is cheaper and works fine for general web servers. SSD provides significantly higher IOPS and is the recommended choice for database servers and any performance-sensitive workloads. Managed disks, introduced in February 2017, are highly recommended. Before managed disks, you had to manually create and manage a storage account for each VM disk. With managed disks, Azure handles all of that automatically in the background. You also get useful features like snapshots and backups at no additional management overhead. The Advanced Options blade also includes networking, extensions, and monitoring settings. For networking, you select the virtual network and subnet you want your VM to join. Assign a public IP address if needed, and optionally apply a network security group. A best practice is to apply the NSG at the subnet level rather than on individual VMs. This ensures consistent, standardized rules across all VMs on that subnet and simplifies management. Extensions allow you to add features to your VM after deployment. You can choose from a set of predefined software packages or execute a custom script. This is useful for installing monitoring agents, configuration management tools, or antivirus software. Auto shutdown is a cost-saving feature that schedules your VM to shut down at a specified time each day. It's perfect for development and test environments that don't need to run 24 hours a day, 7 days a week. You can configure email or webhook notifications to alert users before shutdown occurs. Just be careful, you obviously don't want this enabled on production web or database servers. For monitoring, you can enable boot diagnostics and guest OS monitoring beyond the basic metrics available by default. Both require a dedicated storage account. This is important. Never use the same storage account used by your VM disk for logs. If the VM has disk performance issues, the generated logs will increase disk load, creating an infinite feedback loop that makes it impossible to determine the root cause. Finally, Managed Service Identity integrates your VM with Azure Active Directory for secure, credential-free authentication to other Azure services. And Backup creates an Azure Backup Service instance to protect your VM's data with automated scheduled backups. After your VM deployment completes, you'll notice that Azure has created not just one resource, but 4 separate resources in your resource group. First, there's the virtual machine itself, the compute resource you'll interact with. Second, a managed disk is created to hold the operating system. Third, a network interface is created, which is what connects your VM to your virtual network. And fourth, if you requested one, a public IP address is created. This is what allows you to connect to your VM via remote desktop or SSH from the internet. If you hadn't chosen a managed disk, there would also be a storage account in this list. This illustrates exactly why managed disks are so helpful. They reduce the number of resources you need to track and manage. Once your VM is running, management is organized into 4 sections in the Azure portal. Under Settings, you'll find networking, disks, VM size, security, extensions, and configuration. These are similar to the options you configured during creation. Under Operations, you'll find Auto Shutdown, Backup, Disaster Recovery, Update, Management, and the powerful Run command feature, which lets you execute scripts directly against your VM through the portal, even from a mobile device. Under Monitoring, you can view metrics charts and configure alerts. And under Support, you'll find resource health, boot diagnostics, the ability to reset a password, and the redeploy option, which migrates your VM to a new host if it becomes unresponsive. Monitoring is a critical part of managing your Azure virtual machines, not just for troubleshooting, but for cost optimization. From a metrics section, you can view graphs for CPU usage, disk read and write, operations, and network traffic over custom time periods. If monitoring shows that your VM is consistently underutilized, it's a sign you may be paying for more compute than you need, and you should consider downsizing to a smaller tier. Conversely, if utilization is consistently high, it's time to scale up. One important note: CPU and memory monitoring requires enabling guest-level monitoring separately. Without it, you won't have visibility into these key performance indicators. Alerts are arguably one of the most valuable tools in Azure VM management. You can configure alert rules that trigger notifications when specific thresholds are crossed. For example, you might create an alert that sends an email when CPU usage exceeds 90% for more than 5 consecutive minutes. But alerts can do more than just send notifications. They can trigger automated actions using runbooks. Built-in runbook actions include scaling the VM up or down, restarting, stopping, or even removing the VM entirely. The scale up and scale down actions are particularly powerful. For example, you can create a rule that automatically upgrades your VM to a larger size when CPU hits 90% and then a corresponding rule that downgrades it back when CPU falls below 40%. This is called vertical scaling, and it allows you to pay only for what you use when you use it, while always having enough capacity to handle peak demand. We've covered how to create and manage individual Azure virtual machines. Now, let's move to the next level, building highly available services that can withstand failures. This section covers Azure load balancers, which are essential for distributing traffic across multiple VMs and ensuring your application remains accessible even when individual VMs fail. We'll cover creating a load balancer, configuring backend pools and health probes, setting up load balancing rules, and using inbound NAT rules for direct VM access. We'll also look at the ARM template for deploying a load balancer through code. High availability isn't just a nice-to-have for production workloads with business-critical service-level agreements, it's a requirement. Azure load balancers are the foundation of high availability in Azure. Let's understand how they work and what types are available. The architecture is straightforward. Users on the internet send traffic to the load balancer's public IP address. The load balancer then distributes that traffic across the VMs in its backend pool. In this case, WebSRv1 in Availability Zone A, and WebSRv2 in Availability Zone B. If one VM fails, the load balancer detects this through health probes and routes all traffic to the remaining healthy VM. There are two types of Azure load balancers. A public load balancer routes inbound internet traffic to backend VMs. This is what you'd use for web servers or any externally accessible service. An internal load balancer, on the other hand, distributes traffic between resources within the same virtual network. This is the right choice for database servers or backend services you don't want exposed to the internet. When creating a load balancer, you'll also choose between two SKUs, Basic and Standard. Basic is free of charge. You only pay for the public IP address and outbound traffic. Standard costs more, but supports availability zones, larger backend pools of up to 1,000 instances, and more health probe options. 4. Production workloads with zone redundancy requirements. Standard is the right choice. After deploying your load balancer, there are 4 configuration steps to make it functional. Step 1 is configuring the backend pool. You associate the load balancer with your availability set, then define the network IP configurations of each VM you want to include. In our example, we add both WebSRv1 and WebSRv2 to the backend pool. Step 2 is setting up health probes. A health probe periodically checks whether each VM is alive and responding. You define the protocol, port, how frequently to check, and how many consecutive failures constitute an unresponsive server. 4. Web servers. You'd create probes for port 80, HTTP, and port 443, HTTPS. A common configuration is to check every 5 seconds and declare a VM unhealthy after 2 consecutive failures. Step 3 is creating load balancing rules. Each rule maps a front-end port on the load balancer's IP address to a backend port on the VMs in the pool. You also specify the session persistence model, which determines whether connections from the same client always go to the same VM. Idle timeout can be set from 4 to 30 minutes. You'd typically create one rule for port 80 and another for port 443. Step 4 is configuring inbound NAT rules. Unlike load balancing rules that distribute traffic across all VMs, NAT rule forwards traffic from specific port directly to a single named VM. For example, you might forward port 5589 on the load balancer directly to WebSRv1 for Windows remote management access. The end result: traffic arriving at your load balancer's public IP is distributed across healthy VMs using round-robin. Sessions are maintained, and if any VM fails, it's automatically taken out of rotation. We've now covered virtual machines and load balancers. The final topic in this Module is one of the most powerful Azure features, virtual machine scale sets. While load balancers with availability sets give us high availability, scale sets give us something different, elasticity, the ability to automatically grow and shrink your infrastructure based on actual demand. This section will cover the difference between horizontal and vertical scaling, how to create and configure a scale set, how to define autoscale rules, and how scale sets compare to availability sets, because these two concepts are frequently confused. Let's explore how Azure helps you pay only for what you use, exactly when you use it. To understand Azure VM scale sets, you first need to understand the difference between vertical and horizontal scaling. Vertical scaling, also called scaling up and down, means changing the size of your existing VM. When you scale up, you move to a larger VM with more CPUs, and when you scale down, you move to a smaller one. This is straightforward and requires no application changes. However, there's a critical limitation. Every time you change the VM size, the VM must reboot. This means vertical scaling always results in downtime. For non-production workloads or batch processing, Windows where a brief outage is acceptable, this may be fine. But for services, they need to be always available. Vertical scaling is a problem. Horizontal scaling solves this by adding or removing VM instances rather than resizing. Azure VM scale sets implement horizontal scaling. When demand increases, additional VM instances are spun up and joined to the load balancer to share the workload. When demand decreases, excess instances are removed. At no point does the running application experience downtime. The trade-off: all VMs in a scale set are exact replicas of the primary VM. Changes made by user sessions on one VM instance don't persist to other instances or back to the primary image. This is why scale sets are excellent for stateless application workloads, web servers, API servers, compute workers, but are not appropriate for stateful services like SQL Server or Exchange, where data and configuration changes need to be consistent across all instances. Creating a VM scale set involves 3 configuration areas, all presented in a single screen in the Azure portal. The first area is basic information, very similar to creating a regular VM. You provide the scale set name, choose an operating system image, select your subscription and resource group, specify a location, and set credentials. You can also assign an availability zone. The second area is instance configuration. You choose the VM size, which will be the same for all instances in the scale set. You also set the initial instance count, how many VMs are created up front. You can configure up to 1,000 instances for Azure-provided images or 300 for custom images. There's an important option here called low-priority instances, which uses unused Azure data center capacity and can save you up to 80% on VM costs. However, because these resources can be reclaimed at any time, you should only use low priority for non-critical or batch workloads. Using managed disks is strongly recommended for scale sets. When Azure scales out to hundreds of instances, each with its own disk, managing individual storage accounts manually would be an enormous operational burden. Managed disks handle this entirely in the background. The third area is autoscale rules. You define a minimum, maximum, and initial instance count. Then you create scale-out rules. For example, add 2 VMs when CPU exceeds 75%, and scale-in rules. For example, remove 1 VM when CPU falls below 25%. One critical warning: set your maximum instance count deliberately. A misconfigured rule could trigger rapid scale-out to hundreds of VMs, resulting in significant unexpected costs, even if only running for a short time. When configuring the networking for your VM scale set, you have 2 choices for the load distribution layer: Azure Load Balancer or Azure Application Gateway. The load balancer is free and handles the basics very well. For scale sets, it automatically manages adding and removing instances from the backend pool as scaling events occur, no manual intervention needed. Application Gateway provides advanced features including SSL termination, URL-based routing for directing traffic to different backends, web application, firewall protection, and cookie-based session affinity. It's billed per hour. If your application needs any of these advanced capabilities, Application Gateway is the right choice. On the instance management side, the scale set gives you several powerful tools. You can start, stop, or deallocate individual instances. The reimage option resets a selected VM back to its original default state, useful if a VM becomes corrupted or misconfigured, though it causes a reboot. The upgrade option forces a specific instance to immediately adopt any changes made to the primary image rather than waiting for the automatic propagation process. The scaling blade shows all current scale-in and scale-out rules and lets you add new ones. A best practice is to create separate rules for CPU, memory, and disk utilization. Relying on a single metric can leave you blind to performance degradation caused by a different resource constraint. For example, if you only monitor CPU but a spike in memory usage causes degradation, your scale-out won't trigger and performance will suffer. This is one of the most commonly confused topics in Azure, so let's be very clear. Availability sets and VM scale sets are not alternatives to each other. They serve different purposes. An availability set is about high availability. Its goal is to keep your service running even when individual VMs fail. The VMs in an availability set are independent. A failure on one VM doesn't affect the others. The number of VMs in an availability set is fixed and constant. Azure also ensures that planned maintenance never affects all VMs at the same time. Use availability sets when you have critical, always-on services that need maximum uptime. A VM scale set is about elasticity. Its goal is to automatically match your compute capacity to workload demand. VMs are all replicas of the primary image. They're not independent. If the primary image has an issue, that issue will be replicated to all scaled-out instances. Scale sets are best for stateless application workloads, like web servers, API services, and compute workers. Scale sets are explicitly not suitable for stateful applications like SQL Server or Exchange because changes made by sessions on individual instances aren't replicated back to the primary image or to other instances. There's also an important cost consideration. With availability sets, you're always paying for all your VMs whether they're handling traffic or not. With scale sets, you only pay for the instances that are actively running because instances are started and stopped dynamically based on demand. In many production architectures, you'll actually use both patterns and availability set for your database tier to ensure it's always available, and a scale set for your web tier to handle variable traffic efficiently. Excellent. Let's bring it all together with a summary of what we've covered in this module. We started with Azure Virtual Machines, the fundamental building block of Azure IaaS. You learned how to deploy VMs through the Azure portal, how to select the right operating system, disk type, and VM size for your workload, and how to configure advanced options including high availability, storage, networking, extensions, and monitoring. A key reminder: availability zones and availability sets must be defined at creation time. They cannot be changed later. Next, we explored Azure load balancers, which are essential for building highly available services. You learned how to configure backend pools, health probes, and load balancing rules to distribute traffic across multiple VMs, and how the load balancer automatically redirects traffic away from failed VMs, ensuring service continuity. Finally, we covered Azure VM scale sets, the cloud-native solution for elasticity and horizontal scaling. Scale sets automatically grow and shrink the number of VM instances in response to demand, without any downtime. Remember, scale sets are for stateless workloads where all instances are identical replicas. They are not suitable for stateful services like SQL Server or Exchange. The key best practices to take away: always use managed disks. Monitor multiple resource metrics so you don't miss bottlenecks. Always pair a scale-out rule with a corresponding scale-in rule to avoid runaway costs. And test your high availability configurations before deploying to production. In the next module, we'll explore Azure Storage, security hardening for VMs, and how to use ARM templates to automate your entire infrastructure deployment. Thank you for joining this module.